Hello and welcome to Lecture 3 of Magnetic Interactions in Phys 1204. We've been looking qualitatively at magnetic forces and fields, and in particularly at how to find the directions that they point in. Now it's time to calculate them, which turns out to be in most ways actually easier than figuring out which direction they point in. It's time to finally define the magnitude of a magnetic field, and we're going to work in terms of forces on a straight wire because that's an easy thing to do in the lab. So here's a setup where we have a wire of some length L in a magnetic field, and you can use right-hand rule to verify that the force on it would be out of the page, but we're not really concerned with the direction. Let's focus on the magnitude. And note that these other pieces of wire, which are here so we can explain how we got the current into this wire in the first place, are parallel to the field, and so we know there's no magnetic force on them. So now we can just focus on the force on this one piece of wire. And experiment shows that that force would be proportional to the length of this wire segment and also to the amount of current running through it. And we've already seen that that force depends on the angle theta between the wire and the magnetic field, with the maximum occurring when they're perpendicular. And so to keep our definition simple, we're going to work with the maximum possible force, which is when the wire is perpendicular to the B field. At that point, we can define our magnetic field strength as the force on the wire divided by the length and the current in the wire. Notice how similar this is to our definition of electric field, where we took an electric force on a probe particle and divided by the charge on the probe particle. In this picture, I showed a source object. In this picture, I'm relying on your increasing understanding of the field idea to say that you know that the B field here is due to some sources that are elsewhere that we're not concerned about, and that this B field has nothing to do with the wire that we're using to measure it. And note that we're using a probe current. We would use a probe charge for an E field, but a stationary charge feels no magnetic forces. We need a probe current. And so, as before, we have to divide out everything in the force that's proportional to things that have to do with our probe, so that we get a quantity, the field, which does not depend on the probe we use to measure it. And finally, note that there are no vector symbols here. That doesn't mean this isn't a vector relationship, but the vector nature of it is somewhat complicated. It involves a right-hand rule. I can't just put a vector symbol on the B and a vector symbol on the force. That would imply they're in the same direction, and they aren't. They're perpendicular to each other. Now that we have a definition of magnetic field strength, we can find the units for magnetic field. From the equation, you can see it clearly must be newtons per meter ampere. And we define this as a Tesla, T. A Tesla is a rather large unit. A 1 Tesla field is quite hard to generate. If you measure the field near the surface of a strong rare earth magnet, it's typically around 1/10 of a Tesla. So now if we already know the magnetic field strength from some prior experiment, then we know that for a wire perpendicular to the magnetic field, we can get the size of the magnetic force just by LIB, where all I've done is solved for it out of our definition of the B field magnitude. But more generally, when the current and the magnetic field make an angle theta, we find that the size of the force goes as the sine of the angle theta. Note that this equation is only talking about the magnitude, and that magnitude is positive by definition, and so it's only valid in the range of angles where sine of theta is positive, and so only for theta between 0 and 180 degrees. those calculational methods that I've been over so far are not always the most convenient, and so it's time to meet a new way to multiply vectors together, called the vector product. It's also called the cross product. And when you take the vector product or cross product of two vectors, you get a new vector, which you should contrast with the scalar product or dot product that we've previously seen, where you take the product of two vectors and you get a scalar. So now let's talk about the vector product of two vectors a and b, which make some angle theta with each other. And so we'll say that there's some vector c, which is the cross product a cross b. Well, the direction of c is defined as being determined from the right-hand rule. And so we take our hand and point it along the first vector in the cross product, a, and then we bend our fingers along b, and stick out our thumb, which tells us c, which in this case would give you c pointing out of the screen. And the remaining part of the definition of the vector product is that the magnitude of c is then ab sine theta. This definition of the vector product in terms of using a right-hand rule and this equation for its magnitude is all good and well, but often we don't know the angle between two vectors, and we might not know their magnitudes, although we could certainly get their magnitudes easily. So let's suppose that, as we often do, we know these two vectors in component form. And let's say they're in the xy plane, so they can be written this way. This is just so that I can keep it a little simple. The method I'm going to show still works in 3 dimensions, but as those of you in statics will know, it gets a little messy, and so there are some shortcuts that you can learn. I'm not going to look at the shortcut. But let's just write this all out. So A cross B this multiplication works like any other, where we have to multiply each thing in the first parentheses by each thing in the second parentheses. And so we're going to get now, think about I hat and j hat. I hat and j hat are perpendicular to each other. And so the cross product of them, I cross j, you get from right-hand rule, it will give you k hat. On the other hand, I cross I, well, the angle between them is 0, and sine of 0 is 0, and so I cross I is 0, and similarly j cross j is 0. And using right-hand rule again, you can verify that j cross I is negative k, and so this all comes out like this. And so, as we expected from right-hand rule, c should point out of the screen, and here is how we can get it. So we've already seen that a magnetic force is calculated from a current in a magnetic field acting on a wire of length L, as given here, where that only gives the magnitude, and we have to find the direction by a right-hand rule. But if you compare that with the definition of the cross product, you can see that we can write a magnetic force vector nice and compactly in terms of a cross product of the current with the B field, all multiplied by the length, which is a scalar. Let's just calculate a quick magnetic force. So let's say we have a wire running by a disk magnet, like these rare earth magnets that I used in demonstrating magnetic forces in the previous video lecture. And so the magnetic field, I've said, near a rare earth magnet like this is of order 0.1 Tesla. So in this case here, it would have been a little stronger because of the multiple magnets. But let's work with a wire going by one of these magnets. And with our lab power supply, we can generate a current of about 5 amps. And so let's find the force. And note that the distance here, where the wire is passing by the face of the magnet, is perhaps about 2 centimeters. And that is where the magnetic field is actually strong. The magnetic field is quite weak out over here, and so let's ignore it and just find the force on this piece of wire here running right by the face of the magnet. Well, we know that our magnetic force magnitude is just going to be L I B. In this case, the current is perpendicular to the field, so while there's a sine theta, we don't have to worry about that. Theta is 90 degrees, and so sine theta is 1. And so that's now very simple. We have a 2 centimeter length of wire and a current of 5 amps and a field of 0.1 Tesla, and so that is 0.1 times 0.1, it's about 0.01 newtons. And that is enough to move the wire, as we saw in the demonstration, but note, it's not a very big force at all. I'm going to define the magnetic flux. We're not going to be able to make much use of it for another couple of topic units in the course, but it's defined exactly the way we defined electric flux, and so I might as well define it now because there's really not much to it. So, like electric flux, if we have a uniform field through a flat surface, then we can easily define the flux simply as a dot product of the magnetic field vector with the area vector, where that area vector is a constructed vector that is the size, the magnitude of the area of the flat surface, and is directed perpendicular to the flat surface. But more generally, if we're dealing with a curved surface and or a varying magnetic field, then we have to integrate over the surface in order to find the flux. There is an equivalent to Gauss's law for magnetism, and to see it, you just have to note that there's no such thing as a magnetic monopole. And when I say that, what I mean is that we've searched extensively for them. Here's a recent cover of Physics Today, and experimentally, we have never seen them. We're continuing to search for them, but so far it looks like they don't exist. And so any closed surface we define must contain only dipoles, or of course it could contain no poles at all. That means it contains poles that have field lines coming out of them, and an equal number of poles that have field lines going into them, and so the sum of the field lines out and in must be 0, and so the total magnetic flux through any closed surface is always 0. Gauss's law for magnetism may seem less useful than Gauss's law for electric fields, but it has a very important consequence. It means we can define a flux through a loop. Here's what I mean. Suppose you have a loop. Maybe it's a loop of wire. It doesn't matter. We'll usually think about loops of wire. And it's in a magnetic field. And so you can think about the magnetic field passing through the loop. Or in other words, the magnetic field that passes through a surface, perhaps in the plane of the loop, if the loop is in fact lying in a plane, although it doesn't have to be. But you might worry, if we calculate the flux through that surface, what if we instead drew a different surface bounded by the loop, but not in the plane of the loop? Well, would these have different fluxes through them? Well, the thing to realize is that if you calculate the flux through both of them, you end up with a closed surface. And so the flux through that closed surface must be 0. And that's true no matter what shape you make these two surfaces that are bounded by the loop. Here's a surface. Here's another surface bounded by the loop. That one also has to have 0 flux through it. And that tells us that the flux through this surface and the flux through this surface are the same, and they're the same as the flux through this surface and this surface. And so we can define a flux unambiguously through the loop, because any surface we choose that's bounded by the loop will have the same flux through it.